We're going to talk about real linear programming problem, its application of these things, and then a theory, linear programming theory. I wanted to show you a problem first. I'll walk through it. But for the moment, if you feel that is really difficult, it's okay. This is one of the difficult topics in the first half of the semester. All right, so let's let me see. Delete everything, clear everything, and then we move on to the couple of later slides. This one probably. Yeah, that's the one we can talk about. And you'll have a taste of this problem. It's really long, a lot of words, a lot of information and numbers, and it's difficult to deal with. Okay, so let's read through the problem. Usually it's good to do that. So the New Age Tech App Store is accumulating an inventory of computers and fax machines. The store wants no more than 30 of these two items in the store. On the average, each computer it stocks costs $2,000 and each fax machine $800. The store has set an inventory budget constraint of $40,800 for the two items. If the net profit on each computer is $200 and on each fax machine is $100, how many computers and how many fax machines should New Age Tech App Store have in the inventory to maximize its net profit? All right, so how can we start? Where do we start? After you read through the problem, you start from
Huh?
Yes.
No, I need a plug, like an outlet.
Excuse me. Okay, so you start from the last sentence. Usually it's a question. Okay, if there's a question, you start with this. Or you say you probably will see find blah blah blah, so that you maximize the profit. It is similar. So here is the sentence we're gonna focus on for the moment. How many computers and how many fax machines should New Age Tech App Store have in inventory to maximize net profit? There are two parts I want you to pay attention. One is the first thing, how many computers and how many fax machines. And the second, maximize its net profit. So these two things. The first part, I want you to realize there are two types of things, and we can name two variables in terms of the number of computers and the number of fax machines. So we set let X be the number of computers and Y be the number of fax machines. Okay, so we set up two variables. Next, we wanted to maximize the net profit. So we write to maximize, we're going to express net profit as a function because obviously it depends on the number of computers and the number of fax machines it stores and sell, right? And sales. So to maximize the net profit, you can put P there, that's fine, and net profit. All right, so this is the easier part. Now, the harder part, we need to figure out a function, an expression of the net profit in terms of X and Y. So this is the same. What is the net profit if the store has or sells X number of computers and Y number of fax machines? What is that net profit? So you read the sentence, read the whole problem, and find where the profit is, where the sentence that gives you the information about the profit, which is this sentence. If the net profit on each computer is $200 and on each fax machine is $100, but you're selling X computers and Y fax machines, so the net profit would be 200X plus 100Y. That is our net profit function. We would name such a function the objective function. Objective function. Okay, so this is the objective function, the whole thing. All right. So we have like 2 steps now. First steps, name 2 variables or 3 variables. If there are several more, if there are 3 of them, so you name 3. Normally in 130, in the homework, actually, possibly you have 3. But normally I will give you examples and exam problems like with 2 variables. All right, so you set up variables and then get the objective function. All right, and I want you to write like that. Okay, I want you to write starting from let and then to maximize. Please write these things. If you want to minimize, you write minimize cost C as a function of X, Y. Okay. Now, obviously, we're not going to stop here because if there's no constraint, you just have a more computers, more fax machines, and the net profit would be bigger and bigger and bigger. There's no end, there's no bound. Certainly, that's not the reality. So the reality is that there is some kind of constraints. One, the store wants no more than 30 of these 2 items in the store. Second, there's an inventory budget constraint. Okay. So I'm going to copy down the the objective function, and I'm going to use it later on because this problem is too long and I don't have space to work on it. 200x plus 100y. Okay, I want to maximize that. Maybe I should do not use the whole slide. Yeah, maybe I'll do that. So I have some space to work with. Maybe that's better. Okay. Get rid of that. Get rid of this. I have some space to work with. All right, so we have X is the number of computers. The Y is the number of fax machines. We wanted to maximize the net profit as a function of X. You have $200 for the net profit on each computer, $200. You have 200X plus, and then $100 per fax machine, each fax machine. So we have that. Then we have constraints. We write sub subject 2. Let's formalize this. Okay, that's the procedure I want you to follow. Normally people have here and there, the objective functions here, constraint somewhere else. It's not very organized, which is very difficult for me to find information. All right, so let's follow this nice procedure, and you see those steps very clearly. Okay, so we need to figure out the constraints. The first constraint is that the store wants no more than 30 of these 2 items in the store. No more than will be less than equal to. So less than equal to 30, and the total of them is less than equal to 30. Not one of them is less than equal to 30. So we have x plus y is less than equal to 30. And then we have an inventory budget constraint. So we would have a less than equal to 40800. I mean, it's a inventory budget, so it cannot have more than that money. You cannot hold more fax machines, computers, so that budget is so that the inventory cost is over the budget. You cannot do that. So the cost will be less than equal to $40,800. Then we need to figure out the function of the cost. So you look at the sentence here. On the average, each computer stocks costs $2,000. Now you have X of them, so you have 2,000X. And then for fax machine, $800. Add 800 times Y. That's the cost from fax machine, and 2,000X is the cost from holding X computers. And then there are 2 implied constraints, which is that neither is negative, so it has to be greater than or equal to 0. X and Y have to be greater than or equal to 0. Do not forget that. Okay, don't forget that. It's very easy, just put it there. Otherwise, I'll cut off points. Right? In reality, if you don't put it there, on the theoretical, if you don't put there, the minimum, maximum may be different. So you need to put the constraint there. It's very easy, but don't forget. That's all I ask. If you forget, then if you don't forget, then it's obviously just nothing to think about. Just put it there. In 130, in Math 130, all of the problems we work with, we test you. There are always the non-negative, so you just write them there. In reality, later on, that's a different story. Okay, maybe greater than equal to -3, who knows? But for the moment, in 130, we are dealing with non-negative number of items. Okay, so that's something I wanted to mention. These are the constraints. We have 4 inequalities, like what we did earlier. Okay, so the next step is to draw the feasible region that satisfies all these 4 constraints. That's what we did in the last class. All right, so let's do that. We draw 2 axis, Y, origin, X axis. Let's mark the unit. Don't mark unit 1, 2. Okay, the reason is that at least you got 30. And if you look at this one, if you have a the y-intercept would be around 41. Sorry, 51. So it's really some. It's a little bit too messy if you mark this as 1. Let's not do that. And the x-intercept would be about 20 or so. 24 something. Actually not 20.4, which is not an integer. That's okay for the moment. All right. In reality, if it happens, we're gonna fix it in the end. So for the okay, I think I just accidentally muted myself. All right, so I'm not just mark 10, 20, 30, 40, and 50. This is 10. That's why marking units is important. All right, not always you put dot there and it's 1. So I know this means 10 and 20 and so forth. And here we have similar things. You have let's mark it like that. It's 10, 20, and 30. Okay. Now let's use some scratch paper, some scratch area to work with the first inequality, but first is the equality 30. Pretty easy. X y-intercept 30, x-intercept 30. Because the units are not they're not on the same scale. So even though the slope is -1, but you do see it's not exactly -1. All right, some people X computer wise fax machines. Yes. Right. Is there anything that is not correct here? I think that's fine. There's nothing here. Yeah. All right. So let's draw the line. Okay. And now we mark x plus y equals 30. Get rid of that. And then it's less than equal to, right? And the origin is not on the line. So when I just using the testing point, the origin, 0 plus 0, yes, it's less than equal to 30. So the region that includes the origin would be the right region. It's the half plane. Okay. We'll do that. All right. Now let's deal with the second inequality, but first we have equality. So you have a 2000x plus 800y equals 40800. I'm gonna get rid of 2 zeros. You have 20x plus 8y equals 408. And then I can also divide both sides by 4. I have 5x plus 2y equals 102. Okay. I can divide both sides by a number for an inequality or equality, but never do that to the objective function. Some people say, oh, I have a 200 here, 100 here. I'm going to simplify it to 8x sorry, 2x plus 1y. No, that's wrong. Because this is a function, not exactly equation, even though we mark this NP equals 200x plus y looks like a equation. But if you treat it like equation, you divide both sides by 100, you can, but then you would have a NP over 100 equals 2x plus y. That's really messy. We don't want to do that. So as a simple rule, do not simplify the objective function. Okay, don't do that. But just treat it like that, treat it as a function, leave it there. Okay. While an equation or inequalities, we can make it simpler. These are two big numbers, but they are exactly the same. They are actually equivalent. So I can simplify it like that. That's fine. Okay, now let's find 2 points. The 2 points, you have when x equals 0, y equals 51. When y equals 0, you have 220.4 and then 0. Okay. You may not feel comfortable with that. For the moment, it's okay. In the end, if indeed this will be our solution, we have to mark down. Okay, otherwise it will the cost will surpass the budget. So we're going to deal with that later on. For the moment, we're okay with the fractions. Okay, so we have 51 around that area. That's point. 20.4 is really close to 20. Okay. We don't have to be exact. Mark some because we'll deal with numbers later on, not on the graph. The graph sometimes not very accurate. I think it's okay. All right, so let's put 2000 x plus 800y equals 4800. You can mark this thing there. That's fine. 5x plus 2y equals 102. But it seems to be better to be consistent with the original constraint. All right. And then we see this is less than or equal to, and again, use the origin to test, and 0 plus 0 less than 40,800. That's pretty fine. So the inequality holds. That means the region or the half plane that includes the origin is the right region for this inequality. All right, so we do that. We mark 387. All right. And then we combine the other two inequalities, x greater than or equal to 0, y greater than or equal to 0. That means everything should be on the first quadrant. I can simply draw like that. I don't need to worry about everything to the left. I don't need to worry about everything to the above that. And then this is the boundary we need to use. It's kind of intersection of these two. This part is not good, okay? This part is not good because it doesn't satisfy the other inequality. And then this one. So it's quadrilateral. And then you sort of highlight. I want you to highlight, please shade it. Otherwise, I don't know which one you're talking about. So you need to highlight it or shade it. All right, so far so good.
Yes.
All right, thank you. This is the feasible region. Okay, this is the feasible region. In the homework, in the exam, in the quizzes, don't need to write that. Just highlight the region you want it to be the feasible region. That would be good enough. Okay, I know what you're doing. But if you don't highlight, then I don't know, even though it looks like, it should be, but really you need to highlight. Occasionally you have a feasible region like that, then you really need to highlight. All right. Okay, so here comes the theory of linear programming. There is a project which I want you to explore, read a textbook and explore how the theory would work. So the theory goes like this. If the objective function and the constraints, they are all linear, okay, they're all linear. Here they're all linear. Then the minimum or maximum of the objective function reaches at some corner points. If they have maximum or minimum, then these maximum minimum would be reached at some corner points. What are corner points? The corner points are these things. This is one of the corner point, another one. This is, can mark a little bit better. This one, gee, what's going on? This one, and then this one, this is also corner point. Don't forget that one. So you have 4 corner points for a quadrilateral. And the maximum and minimum of this objective function will be reached at 1 or 2, some of the corner points. Sometimes maybe 2, maybe, yeah, maybe 2, maybe 1. It depends. And in the project, I will ask you to explore these cases, but for the moment, we simply say it will be reached at some corner points. Which one? Well, we're gonna check. The goodness about the theorem is that this is called a feasible region. That means every point in the region would satisfy the constraints. So the infinitely many, there's no way you're going to check 1 point by 1 point. Okay, but the theory says you only need to check these 4 corner points. That's all you need to do. So it's very nice. Now we're going to just okay. So then we need to find these corner points. Then we put them into the objective function to find the maximum minimum. All right, so the next step is to find these corner points. There are 4 corner points. So one of them is very easy, 0, 0, that's the origin. And this point is also very simple. We calculated it, you have 20.4 and then 0. It's not integer, but for the moment, we're gonna leave it like that. And then this point is also easy, 0 and 30. And then this corner point, how can we find this corner point? Can anyone send to me on the chat? How can we find this corner point? Anyone? Somebody said in the chat. Yes, exactly. Find where the 2 lines intersect. So we're going to solve a system of 2 linear equations. That's the last class material. All right. You do need to do that in the quiz, in the exam. Even if you have a graphing calculator, even if you have a graphing calculator, you mark, oh, that seems to be 3, 2, something like that. Oh, well, you need to show me how you get it. That's a part of the things we test you. All right, so let's solve the equations. So these 2 lines, we have x plus y equals 30. And then another one, you can use the original one, or you can simplify it to get to make it simpler. The numbers are not that big, so we divide both sides by 4. 200, I believe it's 200, 400. 400 is okay. So you have 5x plus 2y equals 51. And we did that last time. So you have these two equations. I don't really care about the order and up, above, and below. It doesn't really matter. It's just two equations. You can use the substitution for this one, but I prefer. Hey, I think I made some mistake somewhere. Hold on a second. Hold on a second. Hold on a second. What's going on? 2000x. The fraction 800 divided by 400. You have 2, 400, 5, 400. Oh, that's not right. That's not right. Otherwise, I'll get a negative number. That's 102. That's the right one. Okay, now it's fine. We multiply 2 to the second equation and then subtract this one from there. From the first equation, you get rid of 2y. I have 3x equals 42. And then I get x to be 14. Okay, and then y equals 16. All right. It doesn't look like y is bigger than x, but we have the unit on the y-axis. Look, the length is smaller. This is a piece is smaller, shorter. Okay, so we have 4 corner points, 14 and 16. All right, we're done with that step. I'm going to erase that one. Okay, so next step, a lot of steps. We're going to plug in these corner points to the objective function. We're going to make a table, very simple table. And I'll put corner points, CP, and we have the objective function, and P equals 200x plus 100y. Okay, and I'll list all of them. This all the corner points. To be more accurate, we probably should put 20 there, but for the moment, we're okay. We're not. If that happens to be the right corner point, then we need to make some change. But for the moment, we're gonna just go ahead. And then we have 14 and 16. All right, let's plug in. You got 0. Certainly is not a good solution. And then you have 4080, right? 200 times 20.4, maybe 400 or 4,000. And then we have a 3,000. And then we have what is that? 2800 plus 16 times 16. So you have 4400. And you see, hey, the last one is bigger. So we circle that. This is our maximum. All right, so this is our maximum. And finally, you're gonna answer the question. So you say the store should boom. should have 14 computers and 16 fax machines in the inventory. The maximum profit will be $4,400. Okay, so that finished the whole problem. Okay. This is the typical process of solving linear programming problem. We're gonna test you everything. Okay? All these steps are required to be for you to know. Okay. And again, all right, let's start to review the process. You start with setting up a variables, and then you come up with the objective function. And to write to maximize or minimize. And then you find the constraints, list all of them, and don't forget these two trivial ones. These two usually you need to make some effort, but I hope you're okay with those. And then you draw the feasible region and find the corner points and put these corner points to the objective function. If you want to maximize it, you find the biggest one. If you want to minimize it, you find the minimal one. And then you answer the question. Is the process clear?
Yes.
All right. So we spent like 40 minutes to give one example. All right. So we have got 10 minutes left. So the 10 minutes, we're gonna just work on the setting up. Just setting up, which by that I mean you find objective function and constraints. That's what I mean. And we're not going to solve it. So these equations might have some weird things, but we're not solving them, so it should be okay. I'm going to erase everything here, okay? All right. Let's move back a little bit. Okay, this problem will be in the project, so we're not going to talk about that. Let's look at this problem. Again, we're going to just set up the objective function and then constraints. Of course, you do need to introduce variables. A firm makes a standard and a deluxe model of electric skillet. Each standard model costs $25 and each deluxe model costs $40 to make. The firm must make at least 100 of the standard model and at least 75 of the deluxe. So this is actually individual, not the summation. It's different from x plus y greater than or equal to 175. It's not. Each one has to be bigger. Greater than or equal to 100, greater than or equal to 75. The firm sells each standard model for $30 and each deluxe model for $75, and must have a total revenue of at least $2,250 from sales of two models. The revenue is you need to have some at least. How many of each model should the firm make and sell to minimize costs? All right, so you read through the problem. And then starting from the last sentence, this is the question: how many of each model should the firm make and sell to minimize costs? So two things, right? One, set up variables. Set up variables. So you have two types of models. A standard model. Let's say the number of standard model is X. The number of deluxe models is Y. Okay, so I'm gonna just mark like that. You want to write it, that's great. So X is the number of standard model and Y is the number of deluxe model. We don't have much time for the moment, so I'm gonna just write like that, X and Y. And then we wanted to minimize cost. So you write to minimize the cost C. Again, I wanted to write minimize. If you don't write minimize, just put some functions here and there, and I'll be mad. Okay, I may not cut your points on that, but it's really not good. And you don't have any, if you make the mistakes, I would, just probably should not say that. Okay, so just write that, all right, to minimize or to maximize. So to minimize the cost, so let's express the cost in terms of X and Y. So read the problem again, find where the sentence gives you information about cost. This is a sentence, each standard model costs 25 and each deluxe model costs 40. Some professors or textbooks would write a table. Say, oh, you have a standard model X, and then you have a deluxe model Y, and you wanted to minimize the, so hold on a second, you wanted to find the cost. So each one, the cost 25, each for Y, you got 40. So you have a 25X plus 40Y. All right, that's fine. Okay, that's fine. But not really. It's not necessary. I usually don't, but I don't do that. But if you want to do that, that's okay. But if you think that the table makes you're clear about those messy information, you can adopt that. And then we're gonna subject to, right? To minimize the subject to some constraints. Hold on a second. Yeah, 6 minutes. Subject to. So there's some constraints. Talking about these things. Let's read the problem again. So, the firm must, obviously that's a constraint, must make at least 100 of the standard model. So X has to be greater than or equal to 100. And then Y has to be greater than or equal to 75. And then the firm sells, blah, blah, blah. It must have a total revenue. So you put the revenue somewhere here. Oh, it's a revenue. It's a function, so revenue. And for each standard model, the revenue will be 30. And deluxe model 75. So the total revenue would be 30X plus 75Y. Yeah, you can do that. All right, so it must be at least 2250. You know, at least means, right? You know what at least means, right? Somebody?
Greater than or equal to?
Yes, greater than or equal to. All right, we're gonna do a lot about at least and most in probability. So I really need to know what that means. So now put 30X plus 75Y here. I think we exhaust all the given constraints. There are two implied constraints for this particular problem. It's not necessarily because this X is greater than or equal to 100 already, Y is greater than or equal to 75 already. So this is not necessary for this one. Okay, but normally you should put it there. So that's a setup. All right. I think we, yeah, it's a bit awkward. 1:16. I think we're okay. I'm gonna just let you go. Do you have any questions?
I don't think so. Thank you.
All right. If you don't have any questions, we're gonna stop here. In the next class, we're gonna continue. Okay. We're gonna have a couple of examples of setting up the problem, and then for other problems, we really solve the problem. Homework, do we have linear homework problems as well? I don't think so. So we're gonna have that on Monday. Okay, so today I will assign 2.2. Sorry, yeah, 2.2, which is inequalities drawing those regions.
Professor, I was
Yes.
wondering how we turn in the project 1,
Oh, you just give it to me, paper with paper.
like print it out, bring it to class on Monday.
Yes, if you
All right.
if you really don't want to print it out, you can send me an email and then I print it out. I know you have, it's like it will cost some money, right? Five.
Yeah, it's really not that much, but thank you. Okay.
If you wanted to do that, you can send to me. Okay.
Thanks.
Sure. Other questions?
And did you say it was due on Wednesday or Friday?
Wednesday. That it's normally 1 week after I finished instruction.
Okay, gotcha. Thank you so much. Have a good weekend.
You too. All right. So I see you on Monday and have a safe and nice weekend.
Thank you.
You too.